Hello everyone. Today we solve this question. This question is asked in GATE exam 2023. This question is from functional analysis part. Here this space C01 is the continuous function space whose domain is 01 closed interval and it is a real valued function. The metric in this space is defined in this way. It is called the supremum metric, and fnx are functions, continuous functions which are defined in this way. Fnx are defined fnx equal to x to the power n, and P is a set which contains all these fn functions. Okay, P contains fn, so that n belongs to natural number set. What we can say about this set P, whether this set P is totally bounded, closed or open. What can you say about? Let us check the first option D. It is saying that P is open. Suppose P is open. Suppose P is open. Okay. P open means every point in the set P is a interior point. For example, let F1 belongs to P is an interior point. What this implies? This implies there exists a ball B F1 epsilon which contains F1 and it is a subset of P. This is the definition of interior point. But we know that any ball in the continuous function space is a uncountable set. Uncountable set. This is a standard result. But we know that Fn, here n is a natural number set, so it is a countable set. P is a countable set. This thing is saying that a uncountable set is a subset of countable set. This cannot be possible. This is a contradiction. So our assumption is wrong, means P cannot be open. So option D false. Let us check the option C, whether P is a closed set or not. We know that P is when P is said to be a closed set, P closed set means P closure equal to P. But we know that P closure means P union P dash. P union P dash means the set of limit points. So we have to calculate the limit points of P. If we show that limit points of P is phi, then it can be equal with P and P dash are same. Okay. Our target is to show that P dash equal to phi, means it has no limit point, and P is a sequence of functions. Okay, so if we show that this sequence has no limit point, then we are done. Okay, then we can say that P is a closed set. Here the limit n tends to infinity, fn is what? It gives 0 if x belongs to 0 1, 0 closed interval, 1 open interval, and 1 if x equal to 1. So clearly this limit point function is a discontinuous function. It is a discontinuous function. So if we call it f does not belongs to C01, means f cannot be a limit point. So P dash equal to phi implies P closure equal to P, implies P is a closed set. Means our set P has no limit point, so P is a closed set. Therefore option C is true. Let us check whether P is bounded or not. To check the boundedness, we have to calculate the distance from its origin. We have to calculate D0 Fn. It is the supremum of x belongs to 0 1 0 minus x to the power n mod. Okay, then it gives supremum of x belongs to 0 1 x to the power n. So it gives 1, means any point fn belongs to P lie in the unit radius from the origin. So P is a bounded set. P is bounded. bounded set. Therefore what? Therefore option B is true. Okay, let us check the option A whether it is totally bounded or not. To check option A, we use two standard result. First of all, closed subset of a complete metric space is complete. This is a one result. Okay, and here P is closed. In option C we have proved that P is closed. So, and also we know that the continuous function space with respect to the supremum metric is complete. Means C01 with respect to the D infinity metric, this space is complete. And P is closed. So this one result 1 implies P is complete. P is a complete set. Okay. We will write one more result: complete plus totally bounded implies compact. This is a standard result, compact. But our P set is not compact. Why P set is not compact? Because compact definition of compact set, P equal to Fn, so that n belongs to n. It is not compact. Why it is not compact? This set is not compact because compact set implies that if we take any sequence in that set, it should have a convergent subsequence. But here Fn sequence has no convergent subsequence because the limit point is a discontinuous function. The limit point does not lie in our space, so it has no convergent subsequence. So our set P is not compact. Okay. But if we check the option A, here it is asking about the totally boundedness. Okay. If we take suppose it is a totally bounded set, but we know that it is a complete set because P is complete. If we assume that P is totally bounded, it implies that P is compact, which is not true. Therefore P cannot be totally bounded. Okay. So we conclude that P cannot be totally bounded. So option A is false. So the true options are B and C. Okay. I hope that you all understood it very well. Thank you all.